Okay, I mean, if we're looking at this situation here, yes, I'm only directly pulling on the 10 kilogram mass, but in reality, I'm still pulling all 30 kilograms, right? I've got a 20, I've got a 10. There's this is what we call a system, okay? In all system questions, okay, the net force acts on all the mass. Okay, so anytime we have more than one mass, we have a system, and the net force acts on the combined mass of the system, the net force. Okay, individual forces may act on individual parts of the system. Okay, since the net force acts on all the masses, the acceleration of all the masses has to be the same. Yeah, they can't accelerate at different rates, or they'll come apart, okay, or crash into each other or something. Okay, all the parts of the system have to have the same rate of acceleration, or the system will break. Yes, we're under that assumption. Yes, the string between them is already taut. Yes. Okay. If not, this would become a two-part question. So if there was slack here, the first part of the question would be, I accelerate the 10 kilogram block until this becomes taut, and now it's a system. Yeah. Okay. We don't ever really deal with like this, then that. It's the whole system is going at the same time. Okay. All right. So what we do essentially then in this question is we simplify the system when we draw our free body diagram. Okay, we say that the system is 30 kilograms and that we're pulling this way with 55 newtons worth of force and this way with 44.1 newtons. Okay, that's our force of friction. So our net force is going to be 10.9 newtons. Okay, and that's acting on how much mass? 30 kilograms. Okay. Now, the way they worded this question, that's a little bit more obvious. Okay. The way I would word it, because I'm a jerk, okay, is I would say, what's the acceleration of the 10 kilogram block? Because then a lot of people would throw in 10 instead of 30. Okay, forgetting that this is a system and all of the system has to accelerate. Okay, and then as a result, they wouldn't get the right answer because they forgot that a system acts together. Everyone follow me there? Okay, more of your advanced questions would talk that way. All right, so we've got our 10.9, okay, and we divide that by our combined mass of 30. All right, so we got 0.36 meters per second squared forward, or towards hand, or whatever they gave us there for a direction. Okay. Now, the other thing we can do with the system, as long as we understand all parts accelerate at the same rate, is we could isolate certain parts of the system. If we weren't given information about the whole system, but we were given information about part of it, we could use that information to calculate, let's say, acceleration for one part, and know that that's the acceleration of everything in that system. Okay, so you can use a system as a whole, or you can use the individual parts. Okay, but when we're talking about the net force, we're talking about the whole system. Okay. All right, so with that in mind, I want you guys to try, pen down. Okay, I want you guys to try question number 1 about these two buckets. Okay, so essentially we want to draw a free body diagram again, because that's always the way we want to start these things. Okay, so we're going to have, here's the top bucket. Okay, they're both 5 kilograms. Right, and we know that there's a force pulling up on the top bucket, but we don't know what it is. It never tells us that. Right, we do know that there's a rope that's connecting the two 5 kilogram buckets, and we know that there's a force of 60 newtons up in that rope. Okay, so there's a force of 60 newtons pulling up on the bottom bucket. Everybody okay with that? What force is pulling down on the bottom bucket? Gravity, yeah. And can I calculate that? All right, I can go m times g like we learned yesterday, go 5 times 9.81, and my force of gravity is 49.05 newtons. Okay, so obviously the bucket's going upwards, yes? There's more force up than there is down? Well, because I can't use the 10 because I don't know what this force is. I can't get the net force on the whole system at this point, right? And I need that if I want to use the combined mass of the system. So I was saying before that I can isolate parts of the system and then apply what I learned from those to the whole system, right? Because both buckets are going to accelerate at the same rate. That's the thing we have to recognize with this question is this bucket and this bucket are connected, so their accelerations are identical. I can calculate the acceleration on the bottom bucket because I have enough information to do that, right? So that's what I'm going to do and then apply it, right? All right, so I've got a net force on the bottom bucket, okay, 60 minus 49.05, okay, so 10.95 newtons up is my net force, okay? And that's just on the bottom bucket, not on the system, okay? That net force is acting on 5 kilograms worth of mass. Okay, so I can find the acceleration of the bottom bucket by taking the net force on the bottom bucket and dividing it by the mass of the bottom bucket. All right, when I do that, I'm going to get 2.2 meters per second squared up. Okay, that's the acceleration of both buckets, okay, because they're connected. Does that sort of make sense? Okay, so we can treat the system as a whole as long as we use all the mass, or we can isolate different parts of the system and then apply to the whole system. Right? Okay, so with that in mind, let's look at, have you guys try number 2. So it's going to go back to the example we did here before, okay, with the 2 buckets. So everything is going to be the same, except for what they say is different here. Sorry. The force of friction on the 10 kilogram block is 14.7 newtons. So they're now telling us, all right, here's some differences. Here's individual parts of the system information. Okay, calculate the tension in the rope connecting the 2 blocks. Okay, is one of the things we want to do, and calculate the tension in the rope between the hand and the 10 kilogram block. That's actually the easiest question ever. Anybody know why? Not the same. Actually, part B, you don't even have to calculate. They told you there's an applied force of 55 newtons that's causing the blocks to accelerate. That force is from the hand traveling through this rope here. So I don't know why they asked you to calculate. It's got to be a typo or something, because why would you calculate something you already know? Okay? The question told us that this force is 55 newtons. Okay? All right, I'm going to give you a few minutes to try number 2A there, see if you can figure that out. Remember, we can isolate parts of the system, okay, and see if we can figure that out. I'll give you one more hint. You're going to want to find the tension in this rope using the 10 kilogram block. Okay. You could do it using the 20 kilogram block, but it's a little bit quicker to find it with the 10 kilogram block. Okay. We want to break this system up right now, okay? Because the tension we're looking for is in the middle of the system. We can't find it as part of a whole system because it's smack in the middle. So we have to break it up into the 2 parts so we can isolate that force. Everybody follow my logic there? Okay. So that rope, and this is kind of the nature of ropes and tension, is actually pulling on both the 20 kilogram block and the 10 kilogram block. Okay, that's the nature of ropes. They can actually tension pulls in different directions. But I'm going to look at it from the 10 kilogram block's point of view. Okay, I'm going to draw the free body diagram of just the 10 kilogram block. There's a forward force on the 10 kilogram block of 55 newtons. Okay, they told us that in the question. That's the force that's pulling the whole system, but it's also pulling the 10 kilogram block. Everyone okay with that? Okay, what other forces are acting on the 10 kilogram block? Okay. According to the question, it says there's 14.7 newtons of friction pulling on the 10 kilogram block. Right, so that's another force I've got to draw on here. Okay, what else? There's one more force. What else is pulling on the 10 kilogram block? Yeah, the 20 kilogram block. Okay, I mean, if we were to to pull on one desk, it's pretty easy. But if I tie the next desk behind it to it, it's a lot harder. Okay, because there's another thing pulling on this desk. I don't necessarily feel that. I feel it pulling on this. Okay, it resists me more as a result. Okay, so that additional force is the tension in the string. That's what the question wants us to find, the force in the string between the two boxes. Okay? And it's the only force I don't know for the 10 kilogram block. Okay, with me so far on my logic there? Okay. Did I already calculate the acceleration of this block? Right. Back when we did this example, did we find the acceleration of it? Right. We found the acceleration of the whole system, but it's also the acceleration of this block. Okay. So if we go back to that, right, we know that the acceleration is 0.36 meters per second. All right. So there's another piece of information that I know. So if I know the acceleration of the 10 kilogram block, and I know the 10 kilogram block is 10 kilograms, can I find the net force on the 10 kilogram block? Right? I can go m times a now. Everybody okay with that? Okay. Okay, so F net equals m times a. Okay, so 10 times 0.36 is 3.6 newtons. All right, so that's my net force on the 10 kilogram block. What's the other way to calculate net force? M times a, or what do I do with all these? Add them up. The vector sum of all the forces. So I know 2 out of the 3 forces, and I know what they add up to, 3.6 newtons. Can I find the one I don't have? Okay. This is how convoluted they can get. Remember I warned you about that yesterday? I said it's going to get to the point where you got to really envision and visualize all the forces that you don't necessarily have stated explicitly for you. Okay. That's where Newton's second law gets interesting. I won't say difficult, interesting. Okay, because it's a little bit more involved. All right, so my net force equals the applied force, that's the 55, okay, plus the force of friction, the 14.7, plus the tension, which is what I'm looking for. Okay, so I'm going to manipulate this so I've got tension by itself. So I'll have F net minus FA minus the force of friction equals T. So 55 minus, sorry, not 55, 3.6, sorry. 3.6 minus 55 minus negative 14.7, because friction is backwards, okay, equals the tension in the rope between the boxes, or the other force pulling back on the 10 kilogram block. Okay, so we're getting 37 newtons. We only have 2 significant figures here. 37 newtons backwards. All right. Okay. Now, could I have also done that with the 20 kilogram box? I could. Okay, here's how I could do that. As long as I was really paying attention, okay, they told me the total friction is 44.1. And then in the next question, they told me the friction on the first box is 14.7, which means whatever's left is the friction on the other box. Okay, so we'll just figure out what that is. We'll go 44.1 minus 14.7. Okay, so the force of friction on the second box, the 20 kilogram box, is 29.4. Right, so I set this up in a similar way. I draw the free body diagram for the 20 kilogram box. And I know there's 29.4 newtons of friction going back. What's pulling this way? What's pulling the 20 kilogram block forward? It's the same force we just calculated. It's that string that's between them. Okay, so can I do now a similar thing with this box? Could I say, all right, the acceleration of the 20 kilogram box is 0.36 meters per second squared. Okay, can I find the net force on the 20 kilogram box? All right, I go m times a. All right, so m times a, 20 times 0.36 is 7.2 newtons. All right, so I have a net force on the last box of 7.2 newtons. All right, then I can find T, because F net is force of friction plus the tension. Those are the only two forces acting on the second box. Okay, so F net minus the force of friction will give me the tension. So that's going to be 7.2 minus negative 29.4. Okay, is that going to give me 37 again? Okay, it's going to give me 37 newtons. Okay, exactly the same number. So that string is pulling backwards on the first block and forwards on the second block. Okay, that's the nature of tension. It can actually pull both ways. It just depends on your point of view. All right, everybody kind of understanding me? I'm not going to expect you to be able to like just throw one of those in and do it right away. Okay, but do we kind of see the connections that are going on there? All right. Another type of system is a pulley. Okay. Obviously, we use pulleys to help us to do work. All right, we can use them as force multipliers and things like that if we put them in series. Okay, this is going to be a bit simpler than that. It's just a single pulley. Okay, so if I have that pulley, 25 kilograms on one side, 35 kilograms on the other, and I let it go, what's going to happen? Right, right. The 35 kilogram box is going to fall. The 25 kilogram box is going to go up, and then it's going to smash into the pulley, and things will go south from there. Okay. Is it going to? How fast is it going to accelerate? Decently fast, but is it going to accelerate at 9.81? No, it can't, because the two masses are going to be doing what? Yeah, they work against each other. Okay, so while they're both being acted on by gravity, they're not going to accelerate at 9.81 because one has to pull the other. All right, and obviously the closer they are in mass, the slower that thing would go. Okay, if we had 50 and 1, obviously that's going to go pretty fast. Okay, but when they're close like this, the acceleration is going to be reduced. Okay, all right, so let's have a look at how we would set this one up. It's a frictionless pulley, so there's no friction. They tell us that in the question. We just said the force acting here is gravity. So the force of gravity acts on both of them. Okay, there's a force of gravity on the 25, that should be shorter, and a force of gravity on the 35. Okay. All right, so the force of gravity on one side is 343.35. And the force of gravity on the other side is 245.25. Okay. Are the masses going to accelerate at the same rate? Okay. The last time we had two masses, they accelerated at the same rate. Is this going to be different because it's a pulley, or is it going to be the same? This means the same. This means not the same. What do we got? Same or not the same? Someone give me an answer. Same acceleration or different accelerations? Same. One can't fall faster than the other, or they'll catch one another, right? You ever see something go over a pulley and catch the other thing? Okay? You can't do that. If they accelerate at different rates, either the rope breaks or one catches the other, right? They have to accelerate at the same rate because they're a system. Okay? We're back to that idea that all parts of a system have the same acceleration. All right. Now I want to simplify because I recognize now this is a system. Okay? The combined mass here is 60 kilograms. It's being pulled this way by 343.35. It's being pulled this way by 245.25. Okay? Those are the forces involved. Can I calculate the acceleration of the masses of the system at this point? Okay. Can I calculate net force if I have those two forces? Okay. Okay, so my net force is going to be 343.35 minus 245.25, which should be 98.1 newtons. All right, so there's my net force. That net force is acting on 60 kilograms worth of mass. Okay, so we'll have 98.1 divided by 60. All right, so it's going to accelerate at 1.635 meters per second squared, considerably less than the acceleration due to gravity. Now, acceleration is a vector quantity, and I didn't put a vector on that, and it's still right. How come it can be right without a vector? Right? It's the acceleration of the system. One part of the system is moving down, the other's moving up. I can't put a direction on that unless the question specifies the acceleration of the 35 kilogram mass. Then I would write down. Okay? Or the 25 kilogram mass, then I'd write up. But the acceleration of the system is in different directions. I can only give the magnitude. I can't give a direction because the parts move differently. Okay? Same rate, but different directions. Okay? So with pulleys in all systems, okay, remember, net force acts on total mass. All right, try that one. I'll make it bigger so you can see it. Okay, so we got to identify our forces here. Okay, it says that it's frictionless, so we don't have to worry about any friction within the system. Okay, we do know that pail C is 6 kilograms. Okay, which means that the force of gravity acting on it will be 58.86. Is that right? Okay, newtons. And then we got 8 kilograms here, so that'll be 78.48. Is that right? Okay. All right, 78.48 newtons over here. So obviously the whole system is moving towards the heavier bucket, okay, which sort of makes sense. All right, so we've got the whole thing moving that way. How much mass is there in this system that this has got to move? Okay, we've got 8 plus 6 is 14 plus, yeah, 34. We got another, okay, in here. So we've got 34 kilograms worth of mass. Okay, that's the mass of the system. Right? We can simplify this now and draw it like this. We have 34 kilograms worth of mass that's got to be moved by two forces. Okay, a 58.86 Newton force going this way and a 78.48 Newton force going this way. All right, so I can calculate my net force because those are the only two. Okay, 78.48 minus 58.86 should be 19.62 newtons. All right, so the net force acting on my system is 19.62 newtons. And that's going to be towards the 8 kilogram bucket or left. Okay. So now I can calculate the acceleration. Okay, acceleration is F net divided by m. Okay, so that's going to be my 19.62 divided by the total mass of the system, 34 kilograms. .58 meters per second squared. Okay. Notice that the question said calculate the magnitude of the acceleration of the system. Is that the same logic as before? I can't give a vector on this for what reason? Which way is the 6 kilogram bucket going? Up. Which way is the tire going? Left. And the 8 kilogram bucket is going down. I can't give a vector because they're all moving in different directions, but at the same rate. Okay. So I can only give this unless the question specifies the acceleration of the tire or the acceleration of the 6 kilogram pail or whatever. Okay, that making some sense? All right, you know what? We're going to leave it there. We talked about systems enough for today. You guys can have a little break.